But I mean, I don't know, did you guys feel that this was brutal last semester for those of you that are doing it again, the actual test one?
It got better for me.
Mm-hmm.
But last semester I got like straight up zero. A straight zero for that test one.
Rough.
Yeah. But now it makes more sense now.
Okay. All right. Well, so this is problem one that we're gonna work. It's a straight up, it's actually pretty similar to problem one on the retake. It's a straight up, you have a source, you have a load, and it's a simple transmission line. There's no trick to it. So we're gonna, and the first question is pretty much the same as it was on the original test, find ZL. So let's go ahead and figure out what we need to find ZL. And let me put this guy. And I was writing here some super important formulas that you guys need to know for sure for the test. Like if you are not comfortable using these formulas, you guys are gonna be in trouble. So is there any question? I mean, I know that on our first test, because we were so used to using this formula when tangent was undefined, we were all screwed, but there was another formula that we could have used, which has sines and cosines, and that would have not give you the same error, and you could have go on with your life. Obviously, it's easier to plug these one in your calculator, but if you program them or if you have a code on MATLAB for the test, you just have to plug in numbers, you know? So Z is something you're going to use on every transmission line. You always have to find gamma. You always have to find B naught plus and B naught minus, because if you don't have that, you cannot solve the problem. So I think that if you need to focus on something on the transmission line problems, is on finding those guys, Z in, gamma, B naught plus, and B naught minus, because that will give you your transmission line equation, and that will help you find any voltage at any location on the transmission line.
That gamma is the reflection coefficient, right?
That's right.
Okay.
So let's go ahead and start with problem one. All right, so first I would recommend you to slowly read the question, because last semester there was a question that put two impedances in parallel and I didn't read the question and I just read that there were impedances and I put them, oh no, the impedances were in series. And I just assumed they were in parallel because I didn't read and that took off a good amount of points. So make sure you read the question slowly, okay? Don't be like me. Okay, so so I just finished reading the first sentence. I'm on this sentence now. For you guys, how would you write the length of the transmission line so it actually matches your equations that you've been deriving in this class? So where would you put the 11, or how would you write it down in this transmission line?
Can you repeat the question again?
Yes, so you know that the equations were derived in a certain way, right? Dr. Twacha derived the transmission line equations, which is basically this guy, in a specific way, where you know, here's your length of your transmission line. Where is 0? Where is the length? Is it positive? Is it negative? Do I put 0 here and 11 here? Do I put,
Yeah.
or what did he taught you?
I think generally he puts 0 at the load.
Mm-hmm. Great. So what will make this side?
That's 0 minus L.
Mm-hmm. Which is, based on what they gave us,
My 0 minus to be negative 11.7 lambda.
exactly. That is super important. So this side here is negative, and you will have to do this yourself, okay? He's not going to give it to you. He's either going to give you a random length, or he could be like, oh, this is the length, and he puts a 5 here. What could you do? Because that way it's not derived the way you do it, so you have to put it in a way where this guy is always going to be negative, and this guy is always 0, okay? So make sure you know how to accommodate your length to where you have it in this way, okay? Any questions on that? That is the first and most crucial start of the problem. No questions?
I don't think so.
In the second problem, you have to actually convert one, so you'll get a better look at it when
Yeah.
we go over that problem.
Okie dokie.
Okay, and then you're given this big old thing, which it super scared me, and I skipped this question as soon as I saw that, but I hope you guys are more prepared than I was. So what is that equation? What does that equation actually give you?
It looks like a composition of 2 cosine functions that describe the waves.
Mm-hmm.
So we can get our beta from that, maybe?
Yeah. What else?
You can get a phasor off that.
Mm-hmm. You can get the phasor from here. So this is the time bearing function, and we want to write it in phasor format, right? So if I want to write it
Yes.
in phasor format, which is b of y, right? Because it's not a function of time anymore, it's just a function of position, because that's the whole point of phasors. Then how would I rewrite this? For this, I don't know if you have had quizzes, but you have to use phasor transformations. And if
We
you,
have not had any quizzes yet.
okay, and if you are not familiar, let me find my phasor table that you definitely are gonna need. I'm gonna put it here. This table is straight up from your textbook.
Ow.
And I had it next to me on the test because it's super handy. So just by looking at it, I know my amplitude is 10, which is A. And then I have cosine omega t, and then plus beta x. But here, instead of beta x, what do I have? Well, I hope you can see I have beta y, because instead of x's, I'm in terms of y's. That was not a trick question. Right, so can someone give me the phasor expression of this whole thing? Let's test you on your phasors.
So I have 10 times e to the negative j 2 pi y over lambda
Mm-hmm.
plus 2 times e to j times 2 pi y over lambda minus pi over 3.
Yep, that's right. So let's write it up here. So going back and forth is going to be really important on this test. So we're going to have 10. We ignore the omega t, right? That's not part of us, minus j. Instead of putting 2 pi over lambda, I'm just going to put beta, just like Easton, he wrote the thing there for you. And y? Oh, shit, why is this writing so bad? Now I don't know if you said this or not, T, but I'm gonna go ahead and write it like this. I hope this is what you said.
That's what I said.
Oh, congratulations. Okay, so this is great because now we actually we know the voltage at any point. Okay, you guys understand that? This is the equation to find out the voltage at any point. What do I have to do? I just have to plug in here what is my position on the on the y. Does that make sense? I mean, this is the equation you want to find. This is like your whole goal. And what he did on this question is he like did it backwards. Like he gave you a piece of the puzzle, but you still have to like unwrap it all up. Okay, that's what he does. He's gonna give you a little piece and you have to put the pieces together. Okay?
Uh-huh.
But basically, your goal is to come up with this equation, which is the voltage at any location. That's why there's a y there. So whatever, if we just want to find out what's the voltage in here, right? Let's say that's half of these. So I'm just going to say it's like 5 point something. Then I just plug in here negative 5 point something. And that's going to give me the voltage at that location.
Okay.
All right. That's pretty cool, right?
Mm-hmm.
Okay, now also, does anybody know the actual equation, like without numbers, of that Dr. Twacha derived in class? Like, how does the voltage at any location in phasor look like? Like, does anybody know what this term is, or what this term is?
V0 plus and V0 minus.
Exactly. Awesome job. So the actual equation is right here. It's right here. Right, so if we compare, we can actually see what is V0 plus and what is V0 minus, and that is huge. That's a huge part of this problem. Because if we have V0 plus, V0 minus, we can easily find other shit, like this guy here. Da, 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 da. And what, I mean, in this equation, okay, let me just go back a little bit. What is the first question asking us? Anyone?
It's asking us for the load impedance.
Thank you. Okay, so if we want to find the load impedance based on our equations that we could use, where do you guys see an equation that has a load impedance that we might be able to use?
In the gamma equation?
Exactly. So that tells me in order to use this equation, I need one equation, one unknown, right? And if my unknown is ZL, I need to find what gamma is. But guess what? I know what this is, right? So I can already solve for first part, right? So understanding these guys. So and now I want you to be very careful comparing B naught plus and B naught minus here, okay? So what is B naught plus?
It's going to be that 10e to the negative jby, but it should just be the, I'm not sure.
You're almost there. Yeah, I think you were gonna guess it right if you were gonna guess.
Is it just the amplitude of 10 or is it the whole
Yeah,
thing?
it's
Okay.
just okay. So based on this equation, right, that I have over here.
Mhm.
So only this part, whatever is not e to the negative j beta c is the b plus, okay?
Okay, that's the beta value?
Yeah,
Okay.
sorry if it's, so for that it's b naught plus. Now let's look at b naught minus. B naught minus, careful, yeah, on this one I will warn you, it's not as straightforward. B naught minus, so just what you can do is take away this part and then the rest is b naught minus.
So 2.
No, what else? There's something else besides just beta z in this equation.
So it's 2 times e to the negative 5/3.
Yeah, it's 2
However you do it.
times. And if this makes it easier for you guys, actually, let me do it the nice human being way. So this is nothing but e to the j beta y times e to the negative j pi over 3, right? Oh, shit.
Yes.
That's why. Hold on, let me erase better here. Makes sense? So all of these is b naught minus, okay? Because only this part is not b naught minus, okay?
Okay.
And Dr. Twacha will totally test you on something like this because if he don't understand phasors, he's gonna be pissed at you. Okay, so make sure you are, and if it helps you, you can see it here on our handy dandy list. Everything that the one we just did is this one that is actually highlighted, okay?
He'll also get mad at you for just straight up not understanding the concept, because V0 plus and V0 minus represent the amplitude and the phase shift of the incident and reflected wave. So, for example, V0 minus, it's attenuated a little bit because the amplitude is 2 instead of 10. And then there's also a little bit of phase shift because it's minus pi over 3. So it's got a
Okay.
real and imaginary part to tell you both things.
Yeah, I could not say that better. Okay, so, well, now that you should know B naught plus, B naught minus. From there, remember, okay, so what can you find from there? We just talked about this. Now that we know B naught plus and B naught minus.
We can get gamma.
Yes, so knowing B naught plus and B naught minus, we can get gamma, and we can get ZL from here, right? And I'm not going to go through that. You guys will do it, and I'm just going to give you the answer of what ZL is. So just plug it in your calculator until you get the right answer. So ZL. Now, does anybody know another way to actually find what ZL is? Perhaps a voltage current relationship? What is resistance? Or impedance, I should say, actually. Dr. Twachela has a question.
Voltage over current?
Right. And do you guys remember he also derived the current at the load for you? Because I've been there, I know he just did this. I think it should be fresh in your brain.
I'm gonna be honest. Thursday was a very heavy load in the middle of it.
Well, anyway, so if you have this equation handy dandy, which is only for the current at the load, you could also you already have B naught plus and B naught minus, and you know the characteristic impedance. So what could you have done to find ZL? What would be the expression for ZL in terms of Ohm's law?
IL times VL.
Almost.
It'd be the voltage at the load over the current at the load.
Yeah, division, yeah. So, and do we know the voltage at the load? But can you find it? Where is your equation for voltage at the load?
Yes, we can find it.
Because I'll tell you why. Voltage at the load, what is the location?
0.
Yeah, so B of 0 in that equation that Easton highlighted here, if I plug in 0 for Y, what is my final result? So let's plug in 0 there, what do I get? What is e to the 0 power?
1.
Right, so if I plug in a 0 here, all this thing goes to 1, right? So what is
Yes.
my first term?
10.
Great, okay. Oh wait, let me actually control C. Okay, what about the second one?
It would just be 2 e to the minus pi over 3, right?
It will be 2 times e minus j pi over 3, right? Is this what you said?
Yes.
Okay, and this
Except
is
not the
your,
J.
well, don't forget the j. The j is distributed, okay?
Yeah.
Okay, so this is your voltage at the load. If you find this, so you have so many resources in this little baby equation he gave you. From here, you're also going to find V in, which V in is the voltage. Does anybody remember where is V in?
It's that minus 11.7 lambda.
Yeah, exactly. So you can, having this equation is gold because you can find your B in, which you just replace here, minus 11.7 lambda. Obviously, the lambdas will cancel. Okay, is this making sense?
Mostly, yeah.
Okay, because this is what you're going to be doing on your test. You're going to be trying to find this guy here and plugging in locations that you need. Okay? So if we solve for the voltage at the load, we're going to get a number, and we can also find B naught plus, B naught minus, which we already did. That can help us find I at the load, right? Because it's simply B naught plus minus B naught minus over C naught, right? Which all that is, we know. So finding ZL is easy peasy, right? Any questions on how to find ZL? I gave you 2 ways, not just one, I gave you 2. What was the first way I gave you?
The first way was through the gamma equation.
So you just solve for ZL here, right? And the second way is just solving for current at the load, right?
Yep.
So no surprises, no I'm scared, no nothing crazy, right? Like, oh, it seems pretty easy so far. Why he would never hurt us. And because I'm just going to give you a treat here. I'm actually going to give you the derived equation for finding CL through gamma. Oh, shit. If you ever need to use it, okay? But it just comes from this. Okay, so that is part A. And you guys, I want you to please go through the problems yourself. And if you're not getting the same answers, just DM me on Discord or send me a message on Teams or me or Easton, and we'll see what's happening. But you should be able to just work through it. And another thing that I recommend if you haven't Inspire is store your variables as you go. Like once you finish finding these guys, store it and then put an arrow to the side and say I store it on A, because I mean, on my first test, I stored 16 variables. I'm not lying. It's going to get to that point. And it's going to get very messy, and you do not want to keep writing those numbers again. If you store them, your life is going to be a game changer. Okay? Okay, so part B. We need to find BG. And I saw Dr. Twacha deriving this equation the other day, so does anybody remember what is BGT?
You put the phasor hat and you put time variant.
Oh, sorry. Oh, I need the T, I do not need the hat. That's what we're eventually finding, but we can start with this guy first. Go through your notes, guys. I know you've been taking notes because if you're in class, that's what you do, right? You take notes. So, because what's the point of going to class if you're not going to take notes? Let me see who else is here, because I'm just going to be like the Viragen and ask for a volunteer. That is not Jonas. Well, I don't have a lot of options here. I don't have a lot to work with. Well, T or Drew, it's up to you guys. Somebody has to tell me what BG is.
I'm looking.
Are you asking for the formula for VG?
Yeah, formula, or if you can tell me what it represents, that would be great.
Oh, it's the time varying generated voltage.
Well, yeah, but I want how you find it. What is it? What's the
so you find the
circuit
real
now?
part of the VG phasor times E J to the power of J omega T.
Still not what I'm looking for. Anybody knows how to find BG? There's a formula for it. I mean, I'm going to give you a hint. Okay, I want the formula, but I'm going to give you a hint. It's a voltage divider. Does anyone know why it's a voltage divider?
Can I say it?
Yeah.
It's VG times VG over Vn plus VG.
I think it might be right. Okay, you want to explain why it's a voltage divider, Easton?
Sure. So,
Excuse me.
we were just talking about how impedance is just the relationship between voltage and current. And so we already have looked at the general form for the voltage, which is, V0 plus, V0 minus. But there's also a current one, which is so that's called the wave voltage equation. There's also a wave current equation, which is just describing how both of them travel as a wave along the transmission line. But you can divide the voltage one by the current one and get the wave impedance equation. And that's just like how we were talking about. You can get the voltage at any point along the line with the voltage one. You can get the impedance at any point along the line. And so if you were to look at the impedance, which is just the relationship of voltage and current at this point. Oh wait, Monty, where are you looking on the stream?
I'm
Okay,
looking
I
at
see.
your, I have your box and the.
So if you were to look at the impedance at this point, it can kind of, it's looking at the voltage and current at that point. So I don't know if y'all are in circuits 2 right now, but y'all will learn about 2-port networks. So you can kind of model all of this stuff in this box as one network, like one. So you're just looking at the terminal characteristics, the voltage and current of the network. So that's what the impedance is. So basically this network that I put in the box is summarized by the input impedance, which you have a formula for. So, and then you can just kind of reduce it as a circuits problem here. So if you're looking for, hold on. VG, then all that is, so you can find Vn, which is the voltage along here with the voltage divider. Because all this is if you guys remember circuits, this is just an equation for a voltage divider with this looking at VG as a source and then looking at the voltage across Zn. And then you just simply invert this to find VG. So it'll end up being VG.
I'll write it. I can write it. So,
Yeah, that helps.
Yeah.
But yeah, so it's just, you end up having to invert the formula, but you know that VG, like the easiest way to get to VG is reducing the network all the way down closest to it and then doing that voltage divider. So in the next problem, you'll have to, there's another impedance, load impedance. So you have to kind of work from right to left, reducing the network all the way down closest to the voltage generator so that you can do this same voltage divider to get the generator voltage.
Okay, you guys have any questions on why VG is a voltage divider and how we found it? I mean, this equation, guys, is super important, okay? If you don't know, if you forget everything we just told you and what a voltage divider is, which I really hope you don't forget what a voltage divider is, because Russell will be very disappointed, just write down this formula, okay? And make sure you have it handy on the test. It's super important. It's your VG, it's a voltage divider. And if you're given VG, then you have to solve for Vin, you know, because Dr. Twacha can give you any voltage he wants. He can give you the voltage at the load. He can give you voltage at the generator. Like, he's not gonna stop and give you, I mean, he can give you any voltage, and you should have the tools to solve for V naught plus, V naught minus, and gamma, okay? That is, like, I feel like your goal. All right, so based on this equation, so this is part B. We need to find this VG. So what we know what CG is, that was given to us. We don't know what Zn is, and we don't know what Vn is, okay? But how do we find Vin? And Jonas, you were telling me that earlier.
I was?
Yeah. Remember, we have the equation right here to find the voltage at any location. So what will Vn be?
Oh, it'd be at the negative 11.7 gamma.
Right, so all I have to do is what?
Plug that into the voltage equation.
Exactly. All I have to do is plug in negative 11.7 11.7 here, okay? Be very careful here. I continuously screw these on the test like 3 times because I did not put this negative here, okay? This negative, it's independent of this one, okay?
Okie dokie.
So basically what this says is your location, which goes from 0 to negative. So just remember, if you're not at the load, you have to be a negative number, okay? Unless you're here, whatever you are, you will be negative, okay? So always plug in a negative here. So I don't know if you need to write it down or just you can like be intuitive and say, okay, I'm just putting y at this y position, which is negative, so I know I have to plug in a negative there. Okay, so that's gonna give you B in, okay? Then once you find B in, you also need to find C in, and you're almost done. And I feel like you should be very comfortable with C in already. But if you're not, here are the 2 equations you should write down, memorize. This one is the MVP. It's longer, but it will never fail you, especially during the test where you're freaking out. But here, what's very interesting is here, you never plug in a negative, okay? So I don't know if you want to memorize these or write it down somewhere. In these, when you're finding Z in, this guy is always positive, okay? So here, I'm actually going to plug in 11.7 lambda, okay? So do not confuse these 2 important things. One is this Z in, always positive value of location, okay?
The formulas that have an L in them like that are usually already derived with the negative sign in mind, so you don't have to put it in there. But like the formula for the general wave equation of the voltage that has a Z in there, or sometimes it's a Y, those ones you do have to put the negative sign because those are general and they're not derived in terms of the orientation of the transmission line. But if it has an L in there, you usually don't have to worry. You just put positive value.
Sounds good.
Okay, so we know Z in, B in, we can find BG, right? Which was part B. So I'm just, again, I'm gonna write down the answer here. You guys need to work this out on your own and see if you get the same answer. And if you don't, you're not plugging stuff right in your calculator. So BG ended up being, and like I said, I will recommend you, now that you have, do you have this test?
No.
Not at all? Okay, I will send it to you. I'll put it on Discord. Work this problem. Now you have the answers, and we didn't show you all the work, so that means you can go ahead and do it yourselves. And what I want you to do is do it, store the values as you go, make sure you write your notes of how you're storing the values, how you're recalling them, because if you're not comfortable with your calculator, you are going to get overwhelmed very fast in this test, and it could mess up with your head. So you need to be calm and you need to be comfortable with your calculator, okay?
I don't know what kind of calculators you guys have. I would recommend it even if you have an Inspire, honestly, but especially if you only have a TI-89. Like, Dr. Twacha talks about writing a MATLAB code to solve the problem, which makes it sound like you just put in the values you have and it solves it, but it's really more useful to some of these really important equations. Just put them in MATLAB with something that'll like prompt you for values for the variables, or maybe even use variables that you store in there, just so that you don't have to mess with typing all the stuff in your calculator. Because I mean, even today I was just reworking these problems and I knew how to do the problems. Like I already knew how to do them step by step, but it took me like 2 hours because I was troubleshooting. I kept missing J's or like multiply, like, because I have a TI-89, so it's terrible. So
Oh,
it
yikes.
really helps, yeah, to write a MATLAB code. It'll save you a lot of time in general.
Yeah, I couldn't agree with that more. I mean, especially, I will definitely put the Z in equation there, you know, and just have stuff, or you can, if you have the TI, you can put them in there as well. But MATLAB will save your life for sure. And it's not hard, you know. You just have to make a simple code, or just use MATLAB during the test, and then it will save all your values on the workspace. But either way, just make sure, because it will take time, and you need all these values stored somehow, so you don't have to be also plugging them in as you go in your calculator. And then, so part B was the only hard part of this question, but it wasn't even that hard. So this question was supposed to be very easy. I missed a lot of negatives, and I screwed myself off completely. So I recommend you to just be careful. And then finally, we're gonna find PG and PL. There's no trick to that, guys. All you need to do is plug in and chug. It's the only part, right, Easton, where we advise you to plug in and chug.
Yeah, he does like a whole long derivation in class for the power, and then he's like, but it just happens to look like voltage multiplied by the inverse of current, and then we never talked about it again, so we just used this equation.
Also, a quick pop question. What is I in, or how do I find I in or IL? Don't forget these guys are conjugate. If you don't put the conjugate, you're going to get the wrong value. How can I find I in from what I've just found recently on the test?
We have, hold on.
Oops.
We have the impedance at the input, right?
Mm-hmm.
We have Z in, and we're looking for I in, and we have Vn, so we can just use the voltage current relationship, right?
Exactly. Which is, I just plugged that in my calculator. Instead of putting that, I literally put, and that will be V in over Z in. Same with I load, right? That is nothing but BL times ZL, which we found. We found ZL. I mean, if you did part A, you know what ZL is. Or you could find actually IL, because you have this equation. So there's so many ways to do these tests, okay? Just try to rework problems and see what best you do first, because that's the most comfortable you are with, and you'll be fine. So you know what B load is. B load was right here. And you know what I load is. You know what ZL is. So you can, I don't care how you found the current, you'll be fine. You'll survive, okay? And if you have the TI, the way I plug it in my calculator is like this. I do real, and then I will put whatever variable my VG was stored in. Let's say it was stored in A, and then I do times, conjugate, and then I put my other variables. Let's just say it was B and C. And this gives you that in your Inspire, okay? Does the conjugate. Here's your ratio of voltage impedance, and this was your other voltage. And it makes your life easier, or you can do it in MATLAB. Okay, any questions on how to find any of these?
So, you're putting in B over C as your I in the conjugate, but no, never mind. I see now. Okay, no,
Yeah,
never mind.
I'm just saying if I store them. So let me give you the answer. So PG. Also, put your units. I guess I didn't put units anywhere, and that's mean. She will take points off if you don't put units.
Oh, really? Yikes.
For sure. I mean, if you forget to convert this guy, because this is what you might stop here because you found BG, but that's BG spacer, and you have to find BY of T. So he wants you to convert to this guy.
Okay.
All right. So let's move on to the other problem because that's the one that is going to be the most fun. So I'm actually going to put it here. I'm going to give you a little bit of time if you want to screenshot it or something.
Move it over to the other side of the important formulas so that we can still just look over to them really quick.
Okay. Oh, did you do it? Oh, you moved it? Okay. Let me delete this crap. Let me bring these guys. Oh God, she's hurting. She's hurting because of this. Easton, you're gonna have to move it. I can. I'm so sorry you're hurting, baby. Hold on, let me close this crap. You should hear my fan. Okay, there we go. All right.
Ooh-wee.
Okay, so basically what this problem actually represents is two transmission lines in one problem. You have what I'm gonna call little t, little, how do you spell little?
Prefer little.
No, little scooter and big T. Right, so you have, I mean, you see, this might not happen, depends where this is located, right? But because this length is obviously smaller, that's why I'm calling this little t, okay? I hope that's obvious and not. So, but you have a small one. Come on, you can do this. Okay, everybody kind of sees this. And I know you haven't learned impedance matching. That is not a problem. You should be able to work this problem because it's just two transmission lines stuck together. Okay.
Uh-huh.
Okay, so first things first, I'm going to start writing out the givens. You guys please go ahead and read the problem very carefully while I write this.
So in this problem, you're not given the wave voltage equation like the last problem. And you can get V0 plus and V0 minus, but you can't get beta. So you won't be able to get the wave voltage equation and just plug in how we did on the last problem to get the voltages at different locations. So you just kind of have to think about how the other voltages relate to each other, kind of like on the voltage divider on the last problem, and use the voltages you're given to find the voltages you need.
And actually, in this problem, I would like to go with you guys step by step. So have your calculators out, because I actually now want you, because this problem is a lot more complex. I want to work it out with you step by step and making sure you're getting the shit you need on your calculator. Because if you cannot plug it in, I mean, it's going to take us a while. We might just do the first part, the first half, depending on how we're running on time. But if we can, I would like to start doing so. Take notes, bring your calculator, and be ready. Let me.
I mean, basically, after you do the first part, the rest of the problem is
Yeah.
basically done. That's why it's worth so much. So one of the biggest things is, like, last problem we used this idea to find ZL. The reflection coefficient is, so you guys learned about characteristic impedance in one of the last lectures? Characteristic impedance, a derivation for that, it's based off of like R prime, G prime, and all that, which is all the parameters that model the behavior of the transmission line. So Z0 basically is like, has a lot of good information in it. It's basically the behavior of the transmission line. You'll pretty much always have Z0. And ZL, he probably explained this to you guys, like basically you get reflection when ZL is not matched to your transmission line. So Z0, or characteristic impedance, contains all that behavior for your line. And if your load impedance doesn't match that, then you'll have some kind of reflections because it's at the barrier. It just doesn't transfer correctly. So basically, just know that Z0 and ZL and reflection are all related because of that. So if you have two, you can always find the other one because you'll use that right at the beginning of this problem again.
When you say Z0, you mean the characteristic impedance?
Yes.
Okay.
Yeah, make sure you're comfortable with that vocab, because he's never gonna say, he's never gonna call these guys Zenov. He will call it anything but Zenov, okay? Okay, so do we see what we were given here? The time-varying voltage at the load. Okay, so this is what we're given. How do I write this in phasor? Which is B load, and B load is also B at 0. If you need a phasor refreshment, let me go. Which one am I? Let me ask a volunteer. I don't want to call out names, but it's so tempting.
I know the A thing is the 7 like amplitude, whatever, and like I don't see anything for the beta X, but I think it's just the A cosine WT plus phi naught, right?
Okay, so if we compare, so this is the time varying, and here, thank you, Mark, for volunteer, and this is the phasor here, right? Oh, shit, I'm too far. So if we compare, we have this, which is which one on the list?
The first one.
Yeah, the first one. So in phasor, that's just A, which you're right. It's just the amplitude. So in this case, what will be the phasor representation? Yeah, there you go. Libra, you got this. Okay, and I'm glad you're here because we're just starting this problem and this is the good one. Okay, so that's what Dr. Twache is definitely going to do. He's going to give you time bearing most likely, and you have to put it in phasor first, okay? I mean, look at this. He's going to mix and match. He's going to give you phasors. He's going to give you time bearings. Put them all in phasor so you can get started, okay? So now we have our givens. Now, what was the first thing I told you on the other problem that we need to do before we do anything? What do we want to do to our transmission line? Because this is where I told you he was going to get tricky.
Establish our like where our x0 and stuff is.
Exactly. So I'm just going to cross his line, which I do not like, bad, and I'm going to make mine because I am not going to accept that because that's not what we learned to derive, right? But now I have to establish my length, okay? And that's the first thing you need to do. Establish your own, what is it called? Why can I never think of words?
Axis? Question?
Yeah, guess. Anyway, so what would it look for us? Where do I put the 0?
At the ZL.
Perfect. So what will be XM on our case? So this guy's 0. What is the distance from here to here?
It's 5.4 lambda. No.
I actually think it will be better if we look at his axis, what is the distance from here to here in his axis?
That's 5.4 lambda.
And what's and then he gives you this, which is from X to XL. So he gives you this length and then he gives you this length, right? So he's going to make you think. He's going to hurt you. He's going to spend like 5 minutes already just on figuring out what are your actual lengths.
Another one's 0.75.
Yes. So this guy, if we do just a little bit of algebra, right, we will figure out this is 0.75. Any questions on why this is 0.75? I hope not. I really hope not. But how am I going to write it? Am I going to write 0.75 or what is the whole purpose of this?
I mean, do you want the lambda
in
with
terms
it?
of the load?
So somebody told me this distance a second ago, right? Somebody said 0.75 lambda.
So we write it as negative at xn?
Yes, negative. That's what I was looking for because we want this derivation that we learn in class. The sole purpose of this derivation is that going in this direction, I am negative, right? So first thing I'm going to do is figure out what this guy is going to be, which I already know is just 6.15 minus 5.4, which is 0.75 lambda, right? So what will the point here be? That one should be the easy one.
That's the negative 6.15 lambda.
Yeah, good job. And then this is a step ahead. If you remember to do it right now, it will save you a lot of time in the test. And you will understand why we're doing this right now. You may not understand right as now, but later it will come in why. But I want to know the distance from here to here, which I think it was given to us. So when I break up my transmission line later on into the little and the big one, I want to remember that then when I take this part of the transmission line, I have a distance that goes from 0 to negative. Anyone?
Negative 5.4 lambda.
Yes, excellent. And you will see why we need that later. Okay, so we establish our convention. That's the word I was looking for. So okay, convention. Okay, now, sorry. Now that we established this convention, I actually wrote for you my 3-step approach for solving a problem like this. So take a screenshot of this and then write it later on your notes. This is gonna make sense in a little bit, but if you follow these steps, you will be fine in solving these problems. You just need to be very careful. It's gonna get overwhelmed because you're gonna have so many variables. But if you keep everything organized, you should be able to succeed. So, so we need many things to begin this problem, because let's just look at part A. Determine the voltage at the generator, right? To find the voltage at the generator, I need to break this transmission line into the big one, okay? But to be able to break this transmission line into the big one, I need to find out what the impedance is here. And the impedance here is a combination of Z in, looking into the little transmission line, and this and Z load, which is what I have on my first point, on my first step. First step is find Z in prime, which uses Z knob, which Z knob is the same the whole problem, so you don't really have to stress about that. And the Z load that you are given, hopefully, if you're not given, you're gonna have to solve for it, but you know from problem 1. And you use distance A, okay? So basically what we're doing is taking these two transmission lines and we're gonna collapse. Basically we're combining impedances like we did back in circuits 1, right? So we're just combining those impedances in parallel, okay? So the first step is collapse this part to have an impedance in parallel, okay? And then from that, we can analyze this transmission line and find VG. But doing so is going to require a lot of steps, okay? But the whole purpose, the big picture is I want to take these, combine the impedances, and then analyze just one transmission line, okay?
Okie doke.
Anyone scared yet? Hopefully not. It shouldn't be scary. It's just 2 transmission lines.
Yeah, it's kind of like, it's just the same thing we did on the last problem to find the generator voltage, where you're modeling the behavior of the line, kind of like a circuit element, so that then you can just use your circuit laws that you're familiar with to reduce the network. So you're just modeling that first little segment as one component, like an impedance, and then combining it in parallel. And then you do the same thing for getting even closer to VG. You model the other segment as a component and reduce it. So you'll end up finding VG the same way as the last problem.
Okay, so everybody, okay, so let's just see the first step. The first step is find Z in, right? We know the formula for Z in, and we know we're using the small distance. So I want everyone to be plugging in their calculators. Oh, but wait, can we even find Z in? Do we have ZL yes, we are given C of the load. What else do we need? Do we know L? Don't make me get a volunteer.
Yeah, we know it.
Yeah, we know L. What is L?
That's the 6.15 lambda.
Okay, no, let's go to our first step again.
Oh.
So
Oh, just that part, the 0.75.
yeah, excellent. So we're using the small distance, or what I call distance A. So go ahead and plug it. And if you can, I will just go ahead and store ZL as a variable already in my calculator, because that will make it so much easier to plug it in. And let me tell me what you can use either one formula. Tell me what happens. I'm so curious to know. Anyways, I'll be waiting here. You should have everything you need to find Z in. Are we going to put, in the formula, are we going to put negative 0.75 lambda, or are we going to put 0.75 lambda?
Well, you made it negative, so I'd imagine negative, or is there something beyond that?
Oh, good, Mark. I think you were not here for the first problem, but we were talking that for the Z in formula, your distance is always positive, okay? But for your B naught plus, for this formula, for all these formulas here, or how Easton likes to say it, when you see an L, just plug in the positive value. But for all these formulas here, it must be negative, right? When it asks you for location.
Yeah, when you see L, you can assume that formula was derived by them plugging in negative L and then solving for, because the input impedance is just, it's the basic form for impedance, but they're solving for it at the length. So it's just, they plugged in negative L and that's the equation. So it already considers the negative. But the ones that have the Z, or if it has a Y, that's a general form. It's just any location on the transmission line.
Yeah, and I don't know if, I mean, it might just be me, but I feel like the only time where I see an L is just in the ZN formula. I don't remember seeing it anywhere else. But just know all these guys require the negative. Okay, make a note.
Okay. So all the phasor ones for like the I, the G, the R, so that, and this V, like that wants to take the negative L.
Yeah, you put in negative, whatever you do, because unless you're at the load, which is 0, but anything else will be a negative number.
Is there a reason for that, like with the circuit wise, or is it just like the way we have set for formulas?
It's the way that Dr. Twacha derived the equations. He derived it with this convention in mind, right? That this load was 0 and everything to the left of the load was negative L. So the locations, every time you see something like this, like be at a location, it will be a negative value because you're going to the left.
Okay, thank you.
You're welcome. But Z always put a positive. I feel like Z is the only time where you use a positive, but I could be wrong.
And isn't there like a beta value? Like there's several different like ways with it. Isn't the lambda one like 2 pi over lambda or something like that?
Yeah, let me write it
I don't
here.
have my notes with me at the moment.
And I mean, pro tip, beta equals 2 pi over lambda. So if he gives you a number with lambda, those lambdas are always going to cancel. So if that's the case, I just put straight up 2 pi times the location. Okay? That might save your life. But beta is 2 pi over lambda. Okay, anybody give me their Z in value, please?
When I'm doing it in radian, it's giving me undefined. Is there something in the settings? Because I've done it before, but right now it's not giving me anything but undefined.
Okay, that's great. I'm glad it's giving you undefined because when I did it on the test, it gave me undefined and I plug and plug and plug and try and make sure I was writing it right and it's undefined. And the reason why it's undefined is because tangent, it's undefined at that specific location. So you're never gonna get it. So what can you do? Since tangent is undefined at that location, but that doesn't mean everybody is.
Oh, okay.
That's why we have two formulas for Z in. Everybody used the tangent one because it was so much easier, but until we got to that test.
So I got a 30 minus 40i.
30 minus 40i for Z in. Let me see what it is on polar. Oh yeah, 30 minus 40i, you're right. So that is Z in.
Can you show us the equation again 1 second?
Yeah.
Thank you.
You're welcome. So 30 minus 40i, that's great. So now we can move on. And now that we have that, we can move to the second step of our three-step approach. But actually, let me draw it. So we found so all these impedance here on the little transmission line can be what these points see is this. That's why it's called Z in. It's what these 2 points see. So all these impedance can be simplified to this. So that's why this is what we need to put in parallel with the impedance of the shunt. element, which is Zm. And are they in series or in parallel?
In parallel?
Exactly. So now to find the input impedance, which we're going to call Z prime L. So to find Z prime L, so Z prime L will be, what will be Z prime L, Jonas?
It'd be ZL in parallel with ZM.
So Z prime L will be Z in parallel with Zm. Is that what you said?
Yes.
Okay, good. So that's actually our two-step, our step number 2. Find Z prime L, which is our new Z prime load, which is our shunt element in parallel with Zin, which that was Zin. I guess I'm calling it prime. Let me just, do I want everything on that side to be prime or not prime? I guess I'll put, anyway, so store these values in your calculators and now go ahead and do the parallel combination and let me know what you get and what the value of Zm is up here. Parallel, and hope you all know it's product of the sum. You guys almost found the parallel combination?
Yes.
Okay, what was it?
I got 53.33 plus 40J.
Okay, that's correct.
Can you go over it, how to get that real quick? I'm kind of not sure. I don't think I did it right because I don't think I'd converted it right or something, or I don't know.
Okay, so we need, so you just need to plug it in your calculator. I hope you store this value already. Just store it as a variable. You have the TI, right, Mark?
I do, but I don't know how to store a variable. Like I did like the equal thing, it doesn't store it.
Okay, so write 30 plus J40 and then control and then store because the store is the highlighted. So you have to control and then press the var button. And then type in any character you want. I just do A.
Okay.
Does that work?
Yeah.
Okay, once you store that, then you want to, and then this guy is 40 e to the j pi over 2 Zm, so just write out 40 times e to the j pi over 2 times a, and then over the sum, 40 e to the j pi over 2 plus. Or you can also just do it all by hand. Okay, Mark, let me know if you don't get it, but we're gonna move to here now. So everybody can see that after I found that ZL, I can cut my transmission line in like two separate ones, the little and the big. And this is what the big looks like. And remember I told you we needed to find this length when I make you subtract against your will? That's why we needed to, okay? Because now I have this big transmission line, which now has my impedance all simplified in this C prime L guy. And this is what I'm gonna use to find BG. This is the transmission line I need to use to find BG, okay? But let's think about this. So to find BG, you remember our formula? Let's look, where is the formula for BG? What was BG? We talked about this on problem 1. What is BG?
It's the voltage divider.
So we're gonna need B in, ZG. Do I know B in? No, because I don't know anything about this transmission line. I don't know the voltage anywhere. I don't know Z in of this transmission line. I don't know B in. As a matter of fact, I don't know any voltage of this guy. Not at all, because the only voltage that I was given was which one?
We were given the voltage at the load.
Right, which is the voltage of my little transmission line. So the first thing I need to figure out is if I cut this into the two transmission lines, and this is the little one up here. Also, let me make sure we finish our 3-step program here. Oh, well, the third part was gonna be finding Z in. But you know what? Let's go ahead and find Z in before we even move on.
Also, my ZL prime thingy was like 6.5 plus 22J. So it was way off. I don't know why.
Well, I wrote here what you could type in literally. Make sure you're in radians.
Yeah, I'm in radians.
Make sure you're putting your J. Make sure you put parentheses around this guy. Wait, what?
Yeah, same thing. I have the 6.57 plus 22J.
Is that supposed to be a Z? Oh, a minus? Maybe? Hold on. I guess this is a minus, sorry.
Yeah, if it's minus, it's 53.3 plus 40J.
Okay, good. All right, perfect. Sorry, we now know that where that came from. So, but it's minus because it's this guy, right? That we have here.
Yes.
So I'm gonna put a line here. Okay, so let's go ahead and find Z in. You guys have the formula. You can use either Z in you like, but let's look at the three-step approach. We find Z in of the big transmission line. This is now big, and my distance is now D, okay? So, and what does it say here? I'm using C now, which remains the same, and now C prime L, okay, which is what we just found. So founding C prime L, store this value in your calculator, plug it in here, either formula you like, and what distance are we gonna use?
Use the 5.4.
Yeah, 5.4, and it has to be positive because it's Z in, okay? Let me put my colors correct. Since your L is not 0.75, your tangent won't be an undefined. Pro tip if you want to use the tangent formula, but if you just want to be safe for the rest of your life and use cosine, go for it.
Okay, and the Z L prime is the new ZO, right?
Yeah, which
Or-
is the one we found here. Let me know when you guys find it, please. Whoever finds it first gets a Girl Scout cookie. Got variety over here.
And what was the value that they gave us at the beginning again? For the that we're using as ZL now, because they gave us the other one. I don't see it on screen, or maybe I'm.
Well, the ZL that you're using is this one. The
Yes.
Z knob is 50.
Oh, Z not still 50. Oh, okay,
Yeah.
okay. I got that confused.
So I got 26.278 plus 15.202 I.
26.
Yeah, that's what I got.
Same here.
Okay, perfect. And I'll give me in polar. Make sure you can convert on your calculator in polar. If you have your TI, you do control, and then on the book, I mean, no control, just press the book, sorry, and then P, and then you can find polar.
What was the answer we got?
It was 26.278 plus 15.20J. And polar for me, it gave me e to the power of 0.52 J times 30.35.
Okay, perfect. That's it. You're doing good, guys. Oops. Okay, so let me write it both in polar, and I want to get you used to write it in polar too, because from there it's very easy to see the amplitude and the phase shift in case you need to go to time varying. Okay, so be comfortable going in from rectangular and polar in your calculator.
Okay.
Okay, so Lisa, you want to tell them what they're going to do once they found these three-step approach stuff?
So y'all haven't found any of the voltages, right?
What is the only voltage we know, guys?
The voltage at the load. So for the little transmission line.
Correct. And one thing that's easy to remember, I try not to I don't want to advise you guys to remember formulas, but honestly, that is what you have to end up doing some of the times. This is not a bad one to memorize. Okay, I was trying to see where you were looking.
Wherever you are, I'll find it. I'll find it.
So that just comes from the general equation of the wave voltage along the line. If you plug in 0, which is where we put our load impedance for reference, it just ends up giving you V0 plus V0 minus. So your voltage at your load always equals V0 plus V0 minus, which in this case equals 7 volts. And then from there, the easiest thing to do is factor. Okay, so I think she showed you. Wait, what are you writing out?
Oh, just the general.
Oh, okay. Could you write out if when if you factor out V0 plus right there, how you have e to the beta
the 1
plus
gamma?
plus r. Yeah, will you write that out?
Yeah, so we know these.
But yeah, it's just hard for me to write because I'm on a desktop.
Actually, let me start from here. Can somebody tell me what gamma represents?
The reflection coefficient.
Mm-hmm.
Yeah, so it's the ratio, and this is kind of what I was talking about earlier. So the reflection coefficient is just made up of your load impedance and your characteristic impedance. Your characteristic impedance tells you about the behavior of the transmission line. If the load impedance doesn't match that, you're going to have some reflected wave, and that's what the reflection coefficient tells you. So you can also look at that as the ratio of the reflected wave to the wave that was sent, which is the incident wave. So that's V0 minus and V0 plus. So that kind of comes in handy since V0 plus and V0 minus are kind of used as like coefficients in these general forms. So like right here where I wrote V0 plus V0 minus, it's really just V0 plus and then 1 plus gamma. Yeah, so you don't know that takes it from having one unknown, V0 plus and V0 minus, to just having V0 plus unknown. And V0 plus is also really helpful for finding other voltages on the transmission line. So you already have this because you have the load impedance and characteristic impedance. And you have that VL equals 7 volts. So now you can get V0 plus. And so just kind of like right here where I factored out V0 plus, you can also factor it out on this equation. And so you can get gamma in there and you don't have to worry about V0 minus. And that's actually what you're going to use to employ your V0 plus and find the next voltage you need down the transmission line. So we're given the voltage at the load on the far right, but using this equation right here in V0 plus, we're going to find the voltage at the next load over to the left, so at XM.
And I will remind you guys, finding V0 plus is a big thing on these transmission line problems, because once you find V0 plus, you can find any voltage. You're basically, once you find V0 plus, you're in this equation, which is the equation to find the voltage at any location. And like Easton said, if you put it in terms of B naught plus and gamma, you only have, you have everything you need. You have gamma, you have B naught plus. I think I derive it here. Here it is.
He's going to give you the characteristic impedance every time. And if he doesn't give you the load impedance, it'll probably be one of the first things he's asking you to solve for. Like you'll pretty much like characteristic impedance, load impedance, and reflection coefficient are pretty much three of the things that you're always going to be working it with and trying to figure out how to use them to get other stuff.
Right. So, and what I want you to be comfortable with is that if you have to solve for, if you're given the voltage at any location, you're going to use these two formulas that I have here. If you're given voltage B in or V at a random point that doesn't tell you anything in your life but just your location, once you find gamma, which is your ZL, which you will find somehow, or it will be given to you, you'll be fine, and your characteristic impedance, and then you can solve for B naught plus that way. So if he gives you a random voltage that is not B load, because solving for B plus with the B load is pretty easy, right? You just divide by this, right? Everybody sees that? If I'm given these and I want B naught plus, I just divide by this. It's basically the same for a random location, because you're just going to plug in, you're just going to divide by this term now, though. Where here is where you plug in that location with a negative sign, because locations are negative. Okay, let me Control Z my way out of life. Okay, so now let's think about it. So we were given, Easton already told you what you kind of need to do, but I need you to think. So Jonas, like you're saying, we're given the voltage of the little transmission line. So And I already know I have to break this problem into 2 transmission lines, right? So what other voltage can I find based on what I'm given from the small transmission line? So now I just have this. And I know this is 0.75. So I know the voltage here. I know the impedance here. So basically that tells me the current. But first I need to get to this point first, right? I'm going to call these the little source, even though there's nothing there, but there's a voltage at this point, right? Because we're transmission line, and transmission lines have a different voltage at each location. So if I find this voltage here, which if you look at this transmission line as just one transmission line, this is the generator, right? This is what we call the generator, and it's a negative L, right? But if we then look at the other transmission line, once we found that voltage, what voltage would that be of the big transmission line? So BG here in the big transmission line, which actually become what?
It's the voltage that ZM sees.
Yeah, but once I cut out these, then it becomes, there's a word I wanted to say.
The load voltage?
Yes, exactly. So that is key in these problems. So what is so important about this problem is to understand that this voltage here is the source voltage for the little guy, but it's your load voltage for the big guy, okay? So once you split it, you have to think of these voltages as 2 things, okay? I'm proud of you, though. You're going to earn a lot of Girl Scout cookies today. Okay, so if we analyze only the little transmission line, we have to analyze it and find BG, because BG is then the load voltage of the big transmission line, which we need to find BG for reals, right? So before we can even get to the big transmission line and answer part A, we already have to analyze a transmission line. Before we even get to the real transmission line, we have to analyze. Does that make sense? Which is intimidating in this test, honestly, because it's easy to lose track of what you're actually doing and who belongs to who. But let's recap what we've done so far, because I know we've been on this problem a while, and we probably forgot everything we've done. So the first thing we did was the 3-step approach to understand just the impedances, right? And that helped us break the transmission line into 2, the little one and the big one. And all we did for the big one was find the input impedance and the Z prime L, okay? So once we found that voltage, we already have our Z and our Z prime L, we can find our gamma, and we should be okay. But we need to find the voltage here first, okay? Which is B load of these, but slash BG of little. Okay, so we need to find that. And to find that, we need to analyze the little transmission line first, okay? So let's go to our little transmission line. We're going to put a fake prop there. We know ZL. We know BL, sorry. We know this length. Lambda. Do we have a ZG here? The answer is no, because there's nothing there, right? It's just a short there. So let's start. We have VL, but we want to find the voltage here. So anybody remembers what BG is? We can call this VG prime.
It's that voltage divider again, right?
Right, so that formula is B in times, and you should just memorize this formula. I mean, well, I would love for you to understand where it comes from, but it's just so used that if you just have it written down and know when you have to use it, it will save your life. Okay, so let's simplify this formula a little bit because like I said before, we don't have CG. So if this guy goes to 0, then I have B in times Z in over Z in. And something magical is happening here. So what is VG? You guys don't see the magic, sadly. What is VG equal to?
It's equal to Vn.
Yeah, and we're actually just going to call it VG prime, right? Because this is for the little transmission line. Okay, so all I need to do is find V in because V in is VG prime, which will then be my load for my big transmission line, which is my goal, right? Come back here. This is what I want to accomplish. So if we just find this B in, we're golden, okay? So how do we find B in? What is the equation for B in? It's the voltage we see over here. Or B in is also the voltage at which location?
It'd be the voltage. Are we looking at the little transmission line? Because then it'd be at minus 0.75 lambda.
Yeah.
Okay.
Why would we not be looking at the little transmission line? Though that's my question. Is it clear why we're looking at it? Because we're using just the little transmission line. I want to make that very clear.
Yes.
Okay, I hope there's not. And we know the load, the voltage at the load. So remember, Easton gave you a very important formula. If we're given the voltage at the load, how do we solve for V naught plus? Anyone? How do we solve for V naught plus if we're given voltage of the load? We have ZL, and we have C nub, which means we have gamma. So if we have gamma and V at the load, we have this equation. And what is the only unknown in this equation?
V naught plus is the only unknown.
Right. So can anyone do some algebra for me and tell me what V naught plus is equal to for the love of the world?
Do you want the value in, like, do you want us to solve it and give you a number?
No, just tell me the algebraic expression.
It's just the voltage at the load divided by 1 plus gamma.
Thank you. That was not that hard, right? So remember, your goal is to always find V naught plus. Now, everything we're doing is just for the little transmission line. So when you're solving, because there's like 90% chance you're going to have a problem like this with the impedance matching where you solve two transmission lines. So keep in mind which one you're working on. So all this stuff we're finding is just for the little one. So we're giving voltage at the load, which is equal V of at the 0 location. And we know this is V naught plus 1 plus gamma. And now we know if we want to solve for V naught plus, all we need to do is divide, right? We learned this many years ago, I hope so. And I know everything here. So BL, if you don't remember, it was 7. Gamma is ZL minus C nub, CL plus C nub. And I'm going to go ahead and put primes on everything here because this is for the little transmission line, and I'm putting prime on everything on my transmission line, okay? So just so you remember, this is the little transmission line. So I'm trying to find B naught plus prime. Okay, so you guys can find ZL. ZL was a load that we start with. They actually gave us that value. I will put it again just in case you didn't write it. So go ahead and find your gamma, find your ZL, and find your B naught plus prime for me, please. And why are we solving for B naught plus prime? Because we want to find V in, and we cannot find V in if we don't have B naught plus, right? Because as we know, B naught plus is what tells us the voltage at any location on our transmission lines. It's your goal, okay? Okay, let me know when you find it, please, and give me the value.
You know the value for V naught plus?
Mm-hmm.
Right. So I ended up with 28 over 5 minus 14 over 5i.
Is that your B naught plus value? Is it not like a rectangular or polar?
Wait.
I got 5.6 minus 2.8 J.
Same here.
Yeah, good job, guys. Congrats. Are you proud of yourselves? Now, do you realize you have to do it like 10 times faster for the test? Just FYI.
Oh no.
Okay, so, and let's, you know what? I would like to go ahead and label the steps that we're doing here for the little transmission line. So I think the first thing you did was find gamma, right? Because if you don't find gamma, you cannot find B naught plus. So you did find gamma. Then you found B naught plus. You know which formula to use to do that. And okay, so let's go to okay, so remember, what do I want to find on this transmission line? What do I need?
The VN.
Okay, and how do I find B in? Which formula do I need? Let's go look up here. Which of these looks like I can use? We can do process of elimination. Oops, sorry. Am I looking for ZL? Oh. Am I looking for ZL? No. Am I looking for current? No. Do I need a voltage at the load? I would like you to say no because we already have that, right?
No. Okay.
So I need the voltage at a specific location. And what is that location? B in is always going to be at the most left side of the transmission line, right? So it's just this. Do I know B naught plus?
Yes, we just got that.
Do I know gamma?
Yes.
Do I know what location do I need to find?
Yes.
So can I use this formula?
Yes.
Okay, so let's go to my work. So, oops. So step number 3, find B in. And B in is nothing but the voltage at that location, which is negative 0.75, because we're still on the little transmission line. You guys remember that, right? I haven't told you we're on the big leagues yet, right? Okay, so I hope you store your B naught plus value because you're gonna use it again. Just store it and plug it in that calculator, and your equation, as we just talked, is e to the negative j. Beta is 2 pi. What am I gonna put here after 2 pi? What is my location? Anyone?
Sorry, what's the question?
0.75.
Yeah, negative 0.75. Negative, very important. If you don't put the negative, you're screwed. And then plus. Oh my God, that is ugly. Anybody understands what we're doing? Is it okay? Are we like, okay, that kind of makes sense. I'm not so lost. It's a lot of steps, but if I keep my calm and my cool, I can do it on the test and survive.
I kind of understand, but right now I'm exhausted. But like, I'm pretty sure like I could see all the steps and I get what's going on. I'm
Yeah.
just worried about like making sure I actually know what's going on versus what I think I know and being wrong.
I mean, I feel like, I mean, we've basically used the same formulas over and over, but it's, do you know when to use them? And Mark, you got here a little late, so I recommend you to just rewatch the video because the first part was a little easier to process. It's not so much about the actual hardcore math, but more about like the why behind it. And I think that will help you more because this problem is just so long that it's so easy to get lost. It's very easy to get lost.
No, I'll watch that for sure. Thank you.
Yeah, this one we basically have to work with 2 transmission lines and relate to positions in both of those.
Yeah, I see it. I just could see where I can mess up referring to the wrong transmission line.
Okay, let me guys know when you find your VE, and which is our goal for the little transmission line. All we need to do is get that and we're good. We're so close to the finish line, guys. We're so close.
Okay, I got negative 5.6 minus 4.2J.
I got 2.8 plus 1.4J.
I got negative 5.6 minus 4.2J. So Jonas was right. Sorry. Okay, and anybody remembers why we were trying to find Bein? What is Bein?
It's the voltage at the source for the little transmission line,
Which is?
which is the voltage of the load of the big transmission line.
Oh my god, you're so good. Yeah, that was our whole point. So now that you find your, I want you to like step back and appreciate what we've done in this problem, just so you can have an idea on the test of the steps it takes to do it, okay? And for you to try to keep your cool during this problem and take it step by step. So the first thing we did was the 3-step approach to find them the impedances. And we wanted to find that impedance. Doing that was just to find C prime L. All the 3-step approach does was help you find C prime L, okay? So after we found C prime L, we went to the little transmission line because that's where the information that we're given was. And because we're given the voltage at the load, so we needed to find the voltage at the end location, which is the VG of the little transmission line. But for that, we had to basically solve a full-on problem. We had to find gamma, we had to find B naught plus. I mean, we basically solved this transmission line. But now we're gonna take our reward and bring it to the real deal transmission line that we want to solve. So all this was just to get just a little piece of the problem. But we actually have a lot of information about this problem already. This is the big transmission line, by the way. Remember, we needed to find this length. We already have Z prime L. We've solved for Z in, and now we have BL. So all we need to do is do that voltage divider, and we're done. Right? Isn't that what we keep saying? What is BG? If we want to find BG, voltage divider. So all we need to do is find B in, do our voltage divider, and we are golden. Okay? So basically, and I'm just going to tell you what those steps we need to do. Well, first we need to find gamma. Guess what? That was the first thing we did in this problem, in the little one. Once we found gamma, we need B naught plus. Once we found B naught plus, we need B in. And one step further for the big transmission line will be BG, because BG is actually a real voltage divider, because in the big one I actually have ZG. Does that make sense?
Yes.
So we're basically, literally gonna repeat the same 3 steps we did for the little one, but on the big one and going one more step, okay?
Okay.
All right, let's sharpen our pencils.
I'm using a pen.
Are you crazy? That is so
It's-
disgusting. I don't even want to
It's
see
an
your
erasable
nose.
pen.
Oh, okay. I freaking
I'm not an animal.
Okay, so what is the first thing we want to do in the big transmission line? What was the first step?
Finding a reflection coefficient.
All right, so let's go ahead and find gamma, which now everything for the little transmission line was prime, but now for this one, I'm just gonna go with regular gamma. I hope you're storing your variables, because it's gonna come in handy in your life. And let me know what your gamma is when you guys find it. Your Z naught is still the same. Okay, guys, let me know when you get it. It shouldn't be too hard. You should have all these stored.
I didn't have the correct variable for the last thing because I got like 2.8 plus 1.4. I didn't have it right.
Okay, but for gamma, we're using this guy here. Remember, what was our value for Z? This one.
Okay, using that one, I got 0.15 plus 0.325 J.
Yeah, that's correct. Thank you. That wasn't too hard. Just had to plug in two things. Okay, so you want to ask them what's next, Easton?
Sure. Oh, I don't know where I am on the blackboard. Okay. So you guys just found Vn at XM? Right? Oh yeah, because okay, I see now. So next you're doing, I mean, pretty much the same thing we just did, because this Vn is, where's my pen?
Yeah, where are you? Oh, I see it.
Yeah, this Vn is there a picture somewhere?
To the left of it and to the top a little bit. That's
Okay,
where
yeah. It's just, wait, this picture?
Mm-hmm.
Yeah, the Vn is the same thing as this voltage, the VL. So, and we already talked about how that's just V0 plus V0 minus from, you know, the basic equation. And that's also just V0 plus times 1 plus R.
R. Just kidding.
Or yeah, gamma, sorry. Reflection, excuse me. But and it doesn't, did you guys already find, okay, right? R prime, is that?
So no, you're telling them, yeah, that the next thing they need to find is B naught plus, right?
Yeah, you guys already found this reflection, right, here?
Mm-hmm.
Yes.
Okay, yeah, so all you need to do is find V naught plus, because yeah, you just solve for this voltage, which is basically just a number, and you have this, so you can get V naught plus again, and it's rinse and repeat with the exact same thing you just did, where you're trying to reduce the network down to the voltage divider. So once you have V naught plus, you're going to use it in the, is that a, where's, can you go to the important equations?
Mm-hmm.
You're using the smiley face equation again.
That is your best friend.
Yes, it's a good equation. That's literally just the equation right above it. I'm sure y'all see that. But you just factor out V naught plus and use the relationship, because that's just so they don't have to find V naught minus. It's just the way Dr. Tawacha taught us to eliminate one of the unknowns, because you'll usually have the reflection coefficient. So that's just the normal wave voltage equation in a different form. that is easy to use for this problem and a lot of problems. So yeah, just use the voltage that you guys just found, here for VL, or I guess VL prime, and over 1 plus gamma prime, and that's going to be your new Vn. What were y'all calling the other? Okay, yeah, Vn prime.
I think that was gonna be B0 plus, not B in prime.
Yeah, sorry, my mistake. And you use that to find Vn prime.
All right, so we're literally doing the same step. So we found gamma. Step 2, find B0 plus. And I just saw the formula, so can someone tell me the formula again? I asked this before. I just asked you to do some simple algebra.
The V naught plus is the other V thing of the 1 plus gamma. The V.
BL1 plus gamma, right? Okay, so now you're using your reals gamma, your realsies, and the B load that we found, which is this guy here, that you should store in your calculator. So go ahead and tell me the B naught plus for the big transmission line, please.
I got negative 5.42 minus 2.09 J.
I have negative 5.4 minus J 2.1.
If you round, it's 2.1 for mine.
Okay, fair enough. I'm not gonna put as many decimals, but make sure you put at least 3 or 4 decimals on the test, because Dr. Tuache likes that. Okay, so this is your B naught plus. So once we found B naught plus, what was our third step?
Finding the Vn.
All right, and what was the formula for B in? Easton told you which one to use.
It's the smiley face one.
Okay, so B in. And the way I like to think of these voltages is their voltage at their location. So I know B in is equal to the voltage. Okay, which location am I gonna use? Does anybody know the length that I'm gonna use for the? What location is B in?
The length is like the 6 point something, alrighty? 6.15 lambda.
We'd be using negative 5.4 lambda, right?
Oh yeah,
Right.
sorry. I don't remember.
Yeah. Remember that we shrink these, so this doesn't exist, and we combine those impedance in parallel, so we can reduce it to just this part, right?
Yes.
Okay, so negative 5.4. So let's go to our. So B in is also equal to B at the location negative 5.4 lambda. And this is equal to your equation that you should now be bested with your smiley face equation, which is B naught plus, which you know, e to the negative j theta L. And if you do not put a negative in this L, I'm just going to be so mad at you, okay? Do not forget. And then ej to the theta. So actually, you know what? I'm just going to go ahead and put it for you. I trust you, but
Yeah, because that equation actually has a z, not an L, usually. I think one of the most confusing things for me on this first test was it felt like I was memorizing the equation for like impedance and voltage at the input, and then memorizing the equation for the voltage and impedance at the load, and then trying to like remember like when in reality it's just one equation in different forms. Like you're just using the same wave voltage and impedance and current equations, and you're just using them at different locations. Like it feels like a bunch of different equations, but it's really just the same thing.
Yeah, I mean, I couldn't agree with that more. It's literally this equation over and over again, but I mean, for the most part. But if you have 0, then this goes to 1, and that's your load equation. But it's basically just getting very familiar with this guy here, smiley face. So let me know what you guys get for your V in. I like to say we're about 10 minutes away to finish this problem, or less. Oh, this is part A, by the way. There's 2 more parts.
I haven't been able to get an answer because I got name is not a function error from mine with my stored variables.
Oh, you're probably missing a multiplication sign. That happened to me. I just put a multiplication sign because it might be, if you're putting parentheses, it might try to read it as like f of x instead of like a multiplication. So that might be what it is.
Oh, okay, that's all right.
Yeah. Always, especially with your e to the something, make sure you put the dot once you're going to multiply by gamma, whatever your gamma variable is. And another reason why I wanted to do this problem now with you guys using your calculator is so you can get comfortable with them, because it could save your life.
Yeah, for that I got 4.5097 plus 0.3166 J. If that's correct for VN phasor thingy.
What was it? The second part?
0.3166 J.
Okay, I stored these a while ago, but I think it's pretty much the same answer. I got 0.311999, but it's pretty much the same. I mean,
it could be like the sig figs I use, like, and stuff like that. How many you have put back and oversimplifying or under, I don't know.
Okay, so we found B in, and I'm going to give you the actual polar. Okay, and now what? Am I done? What do I want to find for part A?
We want to find the voltage at the generator, right?
And what is that? We've asked this question 3 times total in this test.
It's the voltage divider.
Great job. So it's V in, Z in, and this, I just remember, just have this formula written down forever, but it is a voltage divider and it's easy to derive it in case you forget, but have it handy. So do we know V in? We just solved for
Yes.
it. I hope you say yes. Do we know ZG?
Yes.
It was given. Do we know Z in?
Yes.
Yeah, it was the third step of the three-step approach we did back in the day, which is over here. And I even label it Z in big in case I forgot when I was taking the test and getting freaked out. And then I forgot where is Z in. I did it so long ago, I have no idea if that's the right one, if that's for the small one. So I just go ahead and label it big. Okay, I bet you forgot you solved for that a while ago.
Perhaps.
I bet you were like, oh, I have to find Z in, I don't know. But no, luckily to you, your past self did. So you know everything. You can thank your past self. So whenever you guys have a chance, please give me the answer to part A of this three-part problem.
So I got 11.25 minus 2.98J.
Yeah, good job. That is the answer to part A. Congrats.
Yeah, he puts like 90% of the work for all three parts of the problem in the first part, so that like halfway through getting the first part, you're like, this is the first part, and you just start crying and don't even finish the rest of it.
That's
I couldn't have said it
cruel.
better. I mean, so let's recap what we did, because I like to step back because sometimes you forget all the work you've done. So when you get this problem with two impedances, first thing you want to do is do your 3 steps to finding Z in. So the first 3 steps we did at the very beginning of the problem was to finding that Z in that came in very handy just right now, right? Because we don't have to worry about that again. We just solve it on the first part of the problem. Then on the second part of the problem, we use the little transmission line. We solve for this voltage. And then on the third part of the problem, we just took it into the big transmission line. He could easily give you the voltage at the generator and ask you for the voltage at the load. And all you have to do is reverse this process. Okay, he's gonna give you random ass voltages. He's not gonna give you, he's gonna give you whatever he wants. I mean, I've seen tests from like semesters, and every test the voltage is at a different location. So make sure you can solve one when he gives you the voltage at the generator. If he gives you so here he gave you the problem 1, he gave you just the voltage at any location. In problem 2, he gave us load voltage. I don't know what the guys are gonna do on Monday, but they might do a voltage at another location. So you'll be in luck to see what you need to do for everyone, okay? But if he had given you BG, then you would have worked with the big transmission line first and then go backwards. Makes sense? Because you would have had to solve for this BL And then you make the connection to the little transmission line, right? The BL of the big transmission line is the BG of the small transmission line.
Uh-huh.
And you would have just solved for B in and etc. So, good job. So we did part A. We can now move to part B. The part B, we're not even going to do it because I know you can. Actually, I'm just going to let you do. I will let you do it with me because I want you to be comfortable plugging in your calculator. So we want to find PG. And we know the formula for PG. Power at the generator. And all you type in your calculator, I'm actually going to type it how you will type it in your calculator. Real BG, which you just found. So store it as a variable, so you can use it here, times. And then you're going to type in conj, which stands for conjugate. And because the formula uses I in, because we don't have to solve for I in, using voltage current relationship, we're going to have V in over Z in, which I hope those are all variables in your calculator. If not, then if you're doing this with another calculator, just remember, do this part maybe first, then find the conjugate of that, and then do multiply by BG, and I'm sure you can do math. Okay, so let me know what you get for PG.
0.853.
That is correct. 0.85 watts. All right, so pretty easy, right? Part B took you literally 2 seconds if you have the variables stored in your calculator, because if you don't, you're so screwed. That's why I really, and also make sure, so calculators in radians, make sure you clear the variables before starting. To clear your variables, I think you just do control clear, or you can also just do menu actions, clear A to Z. And let's do part C, and Houston is gonna do part C for you guys.
So part C is just asking for the reflection coefficient, but it's asking for it at, oops, move the picture, at a certain location. And so it says, determine the voltage reflection coefficient at X equals XM. And so this kind of plays into what I've been talking about with the load not being matched, what actually causes the reflections. So you can kind of think of the voltage traveling down the transmission line normally uninterrupted, and then once it hits the unmatched load, then there's some reflections that occur at that location wherever the load is. So then some of it will be reflected back towards the generator. So it's asking, determine the reflection coefficient at X equals XM. So it's asking for the reflection coefficient considering the waves reflected at that location. So you want to, we found two different reflection coefficients, one for the little transmission line and one for the big transmission line. And the one that we did for the big transmission line is the one that has the load at the location XM. So that's the reflection coefficient you're going to use, because you want to have the reflection coefficient when, like, that's where it's being reflected from. So let me go back down here. Where are you looking, Monty?
I'm looking at the...
Good. So I guess I'll go back down here where y'all were working.
Where do you want to go? I'm on the question. Where do you want me to go?
I was just gonna go down there where y'all were Or wait,
Oh,
where did
okay.
y'all solve for the reflection coefficient?
We here in the big transmission line.
Mm-hmm.
Here where it says big TL.
Okay.
Where there's a smiley face that is not yours.
Yeah. Yeah, so here you can kind of think of like the ghost of the transmission line that we simplified into this network. But it's all like we basically put it in this box, which is ZL. So all the behavior of this is contained in here so that we can look purely at if we send waves, like what fraction of the waves that we send gets reflected back from that location only, because it's asking about at XM, which is at this location. So you want to do it with this network where you're looking strictly at what's reflected from that location. So yeah, you've already solved that. The answer to part C is just the second reflection coefficient you found. So it's this. Because later on your next test, and because he in the last lecture talked to y'all about impedance matching, which I won't get into too much right now, but an impedance matched network looks kind of like the network you're working on right now. There's an impedance somewhere in the middle between the load and the generator. And the point of impedance matching is to maximize the power transfer. So, Monty, will you go back up to like the original picture of like the question?
Yeah, I'm here.
Okay. So, actually, you can think about it because on one of the tests he asked about the power generated, the power delivered here, and then he also asked about the power delivered here. And so if you kind of think about how we were considering this point as the generator voltage when we were looking at this transmission line, that's actually because the way that the transmission works when there's two load impedances right now is you have some power or like some voltage that kind of goes here, and then it might come back and kind of circulate here. And so that creates a voltage here. And so really, when you have two impedances like this, you have a certain amount of power that's transferred here, and then you're trying to transfer, how am I trying to say this? So you'll have a certain amount of power transferred here, and then and that might not be, all of the power, and then you'll have another amount of power being transferred here. So it's kind of weird to think about. It's like some of the power is being transferred here, and then it becomes its own source, and then it's being transferred in this loop. So trying to remember where I was going with that, to be honest.
You were talking about impedance matching and how we want to maximize the power to the load because that's where we want to send the power. But because of the other impedance, we want to match it as close as possible. Otherwise, we're going to have a loss in that section of the line, right?
Oh, yeah, right. Because we were just looking at the reflection coefficient at that point. Yeah, so you're looking for the reflection coefficient at that point because there's its own little behavior going on in this loop. But when you simplify it down to where this is ZL prime, there's a lot of stuff going on here at this point. But when you get down to where this point is ZL prime, it's already considering what's going on in this loop, in this transmission line. So you're just looking for the reflection here. But yeah, that was a very long-winded way to explain how Monty was saying, she was considering this the little transmission line and this the big transmission line. It's because there actually is its own like little loop of behavior going on here and transfer. And so with impedance matching, like when you don't have enough power being transferred here, you put a matching network as close to here as possible so that you have a lot of power transferred here. And then since it's really close, most of that power will also get transferred to your load.
Cool.
All right, so so the answer to C was, yeah, what we found earlier for the big transmission line. So I know this second problem was a lot to take in, but I'm sure if you work the problem, rewatch the video, or just you should work problem 1 now by yourself, and it should be pretty easy after what we did here. So go ahead. Remember, we didn't work out, just give you the answers, and where are the answers? If you want to take a screenshot, Mark, because I know you were not here for this one, but these are the answers for the first problem, and I will post the actual test on Discord so you can download it with just the questions.
Mark's gone.
Oh, okay. Well, he can hear me on the recording. Okay, any questions, guys? I mean, you're gonna be fine. I mean, if you're here, I think you are way ahead of the game, and if you kind of understood what we did or you worked the process, you'll be fine on the test. Just don't stress and try to write as much of your work as possible.
Uh-huh.
All right.
Also, again, MATLAB, if you don't have an Inspire or if you just aren't comfortable saving your variables and stuff, a MATLAB code that'll save your variables for you. And maybe if you already have the equations in there, you can comment stuff in and out as you need it. Like it'll save you a lot of time.
Hey, thanks Monte and Easton for doing this.
Not a problem.
Yeah, thank you.
And you will have another review